And now part of the reason why everything mattered, you can see by the way, part of the reason why everything mattered was I got very little error. I had a little error built into my MATLAB model, because I didn't, but it's not very much. And you can see, look at the MS error is so small it doesn't show up. So that's why these F's are huge and the P's are low. So I said, well, let's, this isn't real data, but let's play like we had an experiment. So let's come over here and let's do this same random trick. Let's put some random number on there like we were measuring with the thermometer, and I couldn't read the thermometer right. The thermocouple's got some error. So you notice this is the clean data. That's the same data that was over here before. 57, yeah, the same data there, but this column I've put some random error on it. So like, see, this one randomly went down, that one went down, that one went up, that one went down, that one went down, that one went up. So I've just added some random, like I had a thermocouple with error. And let's do the ANOVA with something that's got a little more error on it. So let's take this data here and stick it into the same ANOVA. So that's what I did here. And now you see, yeah, our error term's bigger, not a whole lot bigger. But now you can see we get more realistic numbers. Let's see, I guess A mattered and B mattered and D mattered. And then C is marginal. Let's see. Yeah, as we thought, the amount of heat in there mattered, the ambient temperature mattered. Well, the radiation did matter, and the heat transfer coefficient was marginal. And the reason it's not saying it's not important, it is important, but within that range. The range from 1 to what, 7, there wasn't that much difference. So part of what that can help guide you in an experiment like this, in a screening thing, is like, in this case, you sort of told some of the obvious that, well, if I'm gonna spend some money, let's spend some money over with the double E guys, right? And let's nail this. This is one of our important factors. This is an important factor, but what you do, we have no control over it. And then next, well, I guess maybe we should focus a little bit on maybe we should anodize the box. Maybe we should make it black. Maybe we should make it rough. It might help us a little bit. Now we could play with this. Let's see. Suppose I went in here and put a lot. Let's take this really bad thermocouple. Let's see what happens. Yeah, let's try that. I don't know what's going to happen. It may make a backwards point. Sometimes I get the wrong. Let's see. Let's see. So we got really bad thermocouple here. Yeah, let's see. My error went up like we thought. I had more error. It made my MSE go up. And let's see. And so now we've confused and hidden the effect of the heat transfer coefficient and the emissivity. So I would say that's probably more realistic. Those two didn't matter, and again, we're back to, well, the amount of heat loss, the efficiency really matters, and the ambient temperature really matters. And so now, what might have been a better thing to put in, I mean, ambient temperature is kind of a dumb thing to put in because I don't have any control over that. But it illustrates the point. Well, maybe we could postulate that. Well, maybe I do. Maybe I'm gonna put this box in the data center, and I've got an air conditioner, and I can crank the air conditioner down, and have a lower ambient temperature. Okay, that's good. So that tells me that's a good thing. Maybe I should have done an experiment with instead of the ambient temperature, just said that was fixed, and done the density of the air as my factor B. And I can tell you why that matters, because where NREL is, it's in Colorado, and I almost messed that up. When I did all my simulations, I did them with the air here, and one of our younger engineers said something about it. He said, in Colorado the density's less. And I'm like, yeah, you're right, actually. And it turns out that makes about 2 or 3 degrees difference. And so maybe I should have put that one in there, found that out first, and don't do that. But anyway, yeah. So I think one of the things you get from this is at least a feel for what the experiment's like, design experiments like. Let's see, we had the 4 factors. They were related to the real world, right? Heat loss, convective coefficient, radiation, emissivity, and ambient temperature. We had 2 levels, right? And they weren't on and off. They were, 25 and 30 degrees, or they were 0.1 to 0.8 on the emissivity. So you see what I'm doing, and why did I have high and low? Well, I'm trying to span the problem. You know, H being from 1 to 7 was the lowest, the worst I thought I'd get. 7 was about the best, and that, you know, and that also told me, looking and seeing that H didn't matter, for example, might tell me, well, quit worrying about, you know, because we spent some time trying to calculate what H should be and trying to kind of come up with some experiments. Like, hey, you know, quit worrying about it. 1 to 7, so what? Just pick 5 and go on with it. Let's start worrying about other things like the design of the fins on the you know, the little heat exchanger down inside. You know, that you're going to put on the main chips. Don't worry about that. Don't worry about the external coefficients. Just use 5 and be done with it. So I learned some things like that. And then, you know, it gets you an idea of how this works and how this can relate to something in the real world, and how the noise too, you know, the experimental error, you know, plays into here, and how that, you know, kind of hides some of the factors sometimes. You know, and even if we got worse error, it didn't hide the main giant effects. It started to hide these. Well, that's because there's secondary effects and things like that. So you get an idea. And then in this case, you know, this was 1 block out of 2, and we were still able to dig out the main effects. And so you could see, well, imagine that each of these experiments, instead of me just running a MATLAB taking 15 seconds, imagine each of the experiments took a month because I had to make a new box or something. You know, maybe I had to make a whole new box to get a better, you know, to get a better box. Or I had to make a whole new box to get a better convective coefficient or something. You know, so you can see how perhaps you might be forced into this situation where you had to do just a finite number of experiments. You couldn't just sit here, you know, if each of these were months, that's 4 months. And when we did this challenge, we only had a year to get it done. And so, yeah, 4 or 5 months, and, you know, you had to have things done at least ahead of time, or you know, to test it, because you had to provide them with data 2 or 3 months. They screened them. They had hundreds of entrants, and they only screened them, and they only took the top 20. So you basically had to have the thing done about 3 months before it was really due, because you had to send them the package of data to see whether you even, you know, got past the gate. So we did. We made it to the top 20, and then when we sent ours out to NREL, it didn't work. So it's like training for the Olympics, you know, and showing up to run the, you know, the 100-meter dash, and you sprain your ankle in the warm-ups. In our case, we had our main circuit board down in here, and we'd run out of space, so we had a little flexible circuit board. It was a new technology, up to another little circuit board up here. This little flexible thing broke, or when some of the connectors failed, so it wouldn't even turn on. So that's what we get for using some brand new technology. But so we didn't even get off the block. You know, but if you looked at our test that we did, we had about 120 watts per cubic inch. We would have finished in the middle of the pack. Some German company that does this for, you know, their business, they had like 300 watts per cubic inch. They had some disruptive technology completely different from the rest of us. And then the next guys were like 180, and there was a couple around 150 and 140, and then there was us, and then there was a bunch, you know, another 5 or 6 below us down in the 80s and the 90s, and everybody was obviously above 50, or you wouldn't have even made the cut. But anyway, it was a fun thing. So you get a feel for what this is, how this works, how the data is, what the factors are, you know, what the levels are, and how even this stuff actually works. You know, it's kind of funny. I believe, what? I can't believe I throw away a bunch of experiments and still make a conclusion, right? So I guess we're supposed to have a party next time, right? I'm supposed to run Carla and try it. Maybe I'll do that, because then, you know, we won't have to do chapter 10, right? We'll just sit around and talk about it, because we are getting way in the weeds. In fact, I don't even remember what chapter 10, I think, was linear regression. Is that it? Yeah, regression analysis. Yeah, so it's kind of, it takes a different turn, but you know, this got down pretty deep. But hopefully, at least you got to see what aliasing is like and understand what that is, because you're going to hear that. I mean, I hear that all the time in different topics, different areas. Now you at least have sine waves in your line and some green dots on it, and realizing, and you saw mathematically Excel, it showed you exactly what happened. It doubled that coefficient, and yeah, it messed it up. You got the wrong magnitude, and so you can see how that can happen in a real experiment. If you sample wrong, and you get kind of, we were talking in the break, it gets you an idea of why they tell you, you know, your sampling frequency needs to be at least twice as much as the highest frequency thing you care about. Because if you're going to alias, then okay, alias out there in the high frequencies that you just don't even care about. And you're not. That's the same sort of thing as we're doing, picking our blocks such that if we're going to alias, let's alias these dumb things like A, B, C, and D, E, F that we don't care about. Let's alias them. Let's not alias A and B and C. So if you take a Nyquist sampling frequency and you sample it at twice the frequency that you really care about, then all your aliasing is hopefully out here in the high frequencies, and down here in the low frequencies where it really matters and your magnitudes are big, you haven't screwed things up, hopefully. So anyway, everybody have a good Thanksgiving, and we'll be finished for today.